brought to you by Form Systems, the leader in API and cloud gateway technology.
And my name is Paul. I'm from BigML, and the I is for infrastructure. So if you guys all get on the site and start beating it while I'm doing this, that'll be very entertaining. You'll see if we can get my pager to go off. But just to make sure we're all on the same page, I want to start just by making sure that we've motivated this idea of why we even need machine learning in the first place. What's going on here? So imagine that you're working for a telecom company and somebody comes to you and they give you this tiny little data set, all right? And you get some statistics for your various customers, and then there's a flag down here whether or not those customers left. And they say, look, we know there's some information in here that we can get, right? We want to be able to predict which of our customers are going to leave us next month based on this. And this is a very, very small data set, right? But do you guys see any patterns? Right, so the problem is that there's just too many dimensions to really get your head around. I mean, if you play with this long enough, you'll probably get it, even just staring at it, but it's going to take you a little time. But let's actually do it. So I can take this CSV, I can upload it. I'll do this slower. There's the same file, make a data set, make a model. All right. And that's it. So here we have this very strong signal in here, which is that if your customers are texting more than 69 times, they're likely to churn with a confidence of 51%. All right, so that's really a drag and drop in 2 clicks, and the answer comes out. Okay, so the message here is, first, okay, BigML is easy, right? That's part of the message. But really the message is the machine learning is the part that finds these patterns for you and does it in a programmatic way. All right, so you don't have to struggle with, trying to dig into the data. You give it to the machine learning process, and the patterns come out. Why is that important? Well, this was tiny. What are you going to do when there's 100,000 features and millions of rows, right? Now it becomes, even if you could slice and dice this, it becomes impossible. Even worse, what do you do with mixed data types, right? So you got numeric fields, some categorical fields, lists of things, right? Maybe you got some date times thrown in there. And text fields. What are you going to do with those? So these are all the problems that machine learning is going to help you solve. Now I wanted to talk just briefly about the text, because this is the way our text analysis works, and then I'm going to show you guys a demo of our text analysis. So you can imagine you've got this little snippet of text, right? And the first thing we do is something called word stemming, okay, which you find all the root words. Actually, it's language detection, but then once you know the language, you can do this word stemming. And then you're going to throw out these words that have no predictive power because they occur too often, like and, for, the, but. They do it too often. Throw those out. Then you throw out the words that don't occur often enough. Maybe the word some only occurred in this one text field. And then what you're left with is these count of sort of the important tokens that are in these text fields. All right, and then you have these new features. So if you start with a very simple text field, what we're going to do is build thousands of features inside there that are things like the word great appears 4 times. And that becomes now a feature that the algorithm can learn from. So the example I'm actually going to do is one that's from StumbleUpon. You guys familiar with StumbleUpon? Anybody? Yeah, okay, so it's like a content recommender. And they hosted this challenge on Kaggle. And what they wanted their people to do was to build a classifier. Right? So you take all these parameters for websites. How can you parameterize a website? They had things like spelling errors, number of links, the raw content of the site. There's all these other features you can do to parameterize a website. And then they give you this labeled data where each website is labeled as being what they called evergreen or not, which is sort of like, does it have this temporal significance? Okay, so the example I always like to give is, the Wikipedia article on the platypus is still relevant in 10 years, whereas the weather for tomorrow is not, okay? And so we're actually going to run this example. So we'll come back, and now I'll spend a little more time with the UI so you guys get a feel for how this works. So the first step in the workflow is this sources tab, all right? This is where you need to get the data into BigML to do the analysis. And you've already seen one way we can do that, was we can actually just drag and drop. So I have this file here, I'll do that while I'm talking. But you can actually also, you can bring files in with what we call our remote URLs. So you can do, for example, an S3 link or an HTTP link. We also support Azure data blobs and several other other ways to do a cloud-to-cloud transfer. Okay, so you can just put in a URL and the file goes straight over to BigML. So you don't have to bring it down and then upload it back up. We've actually done an integration with Dropbox as well and the Azure data marketplace. So you can pull your files in directly there. Okay, once you've uploaded the file, you can click on it, and what's happening here is we actually just take a peek. We don't analyze the entire file yet, right? Because you could have a huge file, and you don't want to sit here waiting for it. You want to get an idea for what's in there. And this allows you also to set the types. Okay, so you can see we've auto-typed as best we can. I should mention this is rotated 90 degrees. So what used to be rows are now columns. So now we can talk about some of the features that are in this data set. All right, so let's take a quick look here. Okay, so chief among them is this boilerplate. This actually has the raw content of the site. This is one of the features they provide us. And this is, for example, an instance of that data. So it's actually a little JSON document that has the title and the body. Okay, but it's basically the raw content of the whole site. And then they give you things like this alchemy category, which tries to tell you what kind of website it might be. Alchemy category score, how likely it thinks that categorization is correct. Common link ratios, embed ratios, frame-based, etc. So I have all these ways that they've tried to parameterize a website. And then the label, where we're trying to predict 0 or 1, evergreen or not. Okay, so just a simple binary classifier. Now, as you can see, we've got a mixture of text fields, numeric, and categorical. If any of these are wrong, you change them here. Okay, this is where you make sure they're right before we go to our data set. This is a distinction. The reason why these are different is because if you have a very large source, you want the types to be correct before you run this, because now we're actually going to parse the entire file and create all these summary statistics. So the data sets in BigML are like these fundamental building blocks, all right? We use data sets to build models. The clusters, our anomaly detector, you can use data sets to make other data sets. They're the interesting piece. Okay, so for any of these numeric fields, obviously we give you a histogram and some univariate analysis so you can see what's going on in there. For the text field, we'll actually give you a tag cloud. Gives you an idea of the significant tokens in that text field, and you can actually see how many times they're occurring. All right, so we can see these strong signals like recipes in there. And let's do the model. So the only thing we have to do to configure a model is we just have to tell it what we want it to predict and what fields to include. So by default, some of these fields that get left out, it's a little hard to see that. Yeah, so you can see this is grayed out. Okay, so we have some heuristics that help us, sort of determine ahead of time which of your fields might not be useful. Again, this one in particular was left out because it has only one value for every field, so that's not going to give us any information gain, right? So we leave that one out automatically. You see that little exclamation mark? All right, so again, the only thing we need to do to create a model is tell it what we want to predict. In this case, it chose the last column automatically. Okay, but we could easily, turn this data around and we could try to predict the number of links if we wanted to, or any other feature that we thought we might be able to predict. Let's not do that. Let's get straight into the model. So you guys all are familiar with decision trees? I don't want to belabor this too much. Okay, so I'll do my spiel, but I'll do it faster. All right, so we got the root node. Okay, this turned out to be the boilerplate. This is the feature that gave us the best information gain, right? And if we hover over this node, we can see this first branch, right? This is whether or not the boilerplate, so this raw content of the site contains the word recipe. All right, if that's the case, then it's predicting this site is evergreen with a confidence of 86%. Okay, each one of these nodes that are dashed, these are nodes where we've compressed the view so the tree looks nice. All right, there's some branches hidden there. You can see that one was hiding. All right, and any of the ones that are dark circles that are green, okay, these are final nodes. So basically what's happening is that as long as the boilerplate contains recipe and the number 20, and I have no idea why the number 20 is so significant, but there it is, what that's basically saying is that adding, we're predicting evergreen with confidence of nearly 94%, and that adding any additional information doesn't statistically change that outcome. So that's a final node. All right, so in this, and I forgot to mention, I'm going to go super fast. So if you guys, so feel free to look confused if I'm going too fast. Yes, so this is one visualization we have. You can also go in here and you can filter by the predicted outcome. I forgot to mention these trees will also do regressions. And although this is a binary classifier, you can do multiple classifications as well, right? So you can have 10 fields and it'll go through and predict all those classes. That's no problem. It's easier to explain binary classifiers though. So let's just come in real quick and I'll show you this sunburst visualization. Okay, so if you just took that tree and rotate it, so you're looking down on it, right? This root node is this center circle. Okay, and the first arc, or the first circle outside there is that first split. I see this little arc segment here is boilerplate, contains recipe, and this longer one over here is doesn't. Okay, the arc length is proportional to support. Okay, so you can see that there's 500 instances in that arc and 224 over there. And this right now is colored by the confidence of this model. So this gives you a nice way, before some of the branches are hiding, you're clicking around, you're not really sure where things are. This way you can see the whole tree all at once. And so any of these parts that are red are where the model is struggling, is trying to add more information, get better confidence. And parts that are bright green are the confident predictions. So we can see this is that same two-step branch that I showed you, is that segment right there. We can change the color, and we can color it by the class. Right, so now the dark blues are the predicting a label of 1, and light blues are predicting a label of 0. You can even color it by the split field, so now you can get an idea overall how what features the tree is using to make its decisions. So here we can see, you can't. There we go. Yep. All right, so far all we're doing is we're just exploring the tree. There's lots of things you, of course, can do with this tree. I did want to show you this model summary report. So one of the things that we do is we actually look over the entire tree at how much each of the features is contributing to reduce the error of the model. And then we weight those, and we give you this nice ranking, okay? So we can see here the boilerplate is a very dominant feature in predicting this, the class that we want. And this is very useful because sometimes when you're approaching this, you don't really know what the features are that are going to be helpful. All right, so you come in here, you do this analysis, and this kind of falls out for you. This is telling you, if you go back, maybe you can spend a little more time with that boilerplate. Maybe you can get some more information out of there. It's a very strong signal. And the stuff that's way over here on the right-hand side is not potentially very useful, like this compression ratio. Okay, this is a 0.2%. This is compression ratio you could probably imagine is something that might be expensive to compute, and maybe you stop because that feature is not helping you very much. Okay? It's more significant when you have 100,000 features. Of course, we can use this model now to make a prediction. Predict. That screen is off, by the way. Or not. Well, I'll show you this. So one of the things that distinguish us from a lot of machine learning platforms is that the models that we create are fully extractable. We don't restrict them at all. Okay, and it's an advantage of decision trees as well that they're basically just conditional rules, right? They're if-then-else rules. And so we can come in here, we can actually see what this decision tree would look like expressed, for example, as Python code. Oh, connection error. 1 second. So we can see this decision tree, for example, expressed as a Python function, very easy to do, or Ruby or any other language that you'd like. We provide exports for. So what this means is that you can take this model out and you can use it in your edge location to make predictions locally. You don't have to use us for predictions. Okay, and we actually make this very easy in the bindings. As you can even extract these models, instantiate them as a local object, and you can make predictions in your local environment directly with the Python bindings or the Node.js bindings, or probably a few of the others. So now I'll show you the prediction. That'll work better. All right, so we create this nice little form. The text field gets a text box. That makes sense. I like pumpkin pie, so let's put that in there. And you'll notice that these predictions, we're making a prediction at the top there. So for this data, we're predicting a label of 1. And you'll notice that it's changing in real time, right? As I change these fields, that prediction right there, and it's changing fast, okay? So the internet's not that fast. Sorry, guys, latency. But this model, we actually extracted it, okay? And it's running in the JavaScript in my browser. I mean, so that's an example of what you can do with the extractability of our models, okay? All right. Well, let's come back to this model for a second. And how do we know this is doing anything at all, right? I mean, it looks good. I'm pretty convincing, I know. But there's a question, which is, if we just gave it coin toss data and asked it to predict the stock market, it would build a tree, and you'd navigate and be like, sweet, if I get 3 heads in a row, Apple will be over $800. I mean, it's gonna try to fit the data you give it, even if there's nothing in there to fit. Right? So how do you know if it's doing anything useful at all? Well, this is this idea of evaluations coming in. Okay, so the traditional way you do this, you start with your single data set and you're going to split it. Okay, do a training set and a test set. And you're going to build a model off the train set. And then you're going to use that model to generate predictions over the test set. You know all the answers in the test set, so you can compare the predictions to the known answers and just look at an absolute count of how many times you got it right or wrong. Okay, this at least gives you some kind of statistical idea of how well your model is doing, if it's giving you any information at all, anything useful. Fortunately, this is quite easy to do. We can come back to our stumble upon data set here, and we can actually just do a one-click training and test split. Right off the menu there. And if I go back out to the data set view, you'll see we have two new data sets now, test and training. So it does an 80-20 by default. I'm just going to take a one-click model off that training set. So now I'm building the model just over 80% of my data randomly. Randomly selected data. Just glad it's not the site. That's good. All right, so from the tree now, what we can do is we'll just choose this evaluation option here. And all that's happening here is that on the left-hand side, we're choosing the model, on the right-hand side, the test set that we want to run it over. Okay, so you could have your own test set, for example. We didn't provide one, though, so we'll go ahead and use... I forgot to mention, it automatically, since we did a training test split, it knew that we probably wanted to use the test set. All right, and then what we do is we give you these... This is a classification problem, so we give you these 5 metrics here, which are accuracy, precision, recall, F measure, and phi. Okay, so accuracy, this is what you might expect, when you're in college, right? This is like, it's your test score. It's just... Everybody loves accuracy. It's not always the best measurement. It depends on what you're doing. All right, which is why you have these other fields as well. And I think my time's running short, so I'm going to go even faster here. So how do we, what does this mean? Accuracy of 68%, is that good or not? This is one of those things like, okay, for example, if you're doing a fraud analysis, right? So if I give you 100 instances, okay, 99 are not fraud and 1 is. All right, I could give you a model that just ignores the input data and says it's not fraud, and that model would be 99% accurate. So that's a perfect example of, interpreting these metrics, you usually have to have some understanding of what it is you're trying to do. In this case, that's not bad. It's not a great score for this particular classification problem, but it's not bad. We can do better than that. But the other thing is that we do provide some baseline metrics for you, right? So you can compare this to the mode. Right? So this is essentially what I was just describing before. It's like if you just took the most common class and then random as well. So as long as you see, some improvement over those two baselines, right, then your model's probably finding at least some signal in your data. Okay, it's not completely random. There's something happening there. But now, of course, the real strength is that we can go back and we can try a different approach, right? We could leave some features out. We could try adding some features. We could evaluate again and see if we get better. Okay? So what's something easy we could do to improve the accuracy of this model? Well, the answer is ensembles. So let me just explain ensembles. So imagine you had this really big data set that's trying to predict what kind of fruit you have based on the diameter in centimeters. I forgot to put the unit on there. My physics professor would be very upset. And the color and the shape, all right? And you can kind of see in this data set, if you're looking at this, you have this really big plum, right? It's an outlier, okay? No one's ever seen a plum that big. It's really rare. So if you built a model using all those data sets, they're all gray because I've highlighted them, I'm selecting them all, and you ask this model, what's a round, red, 6-centimeter fruit? It's probably going to say a plum, right? In fact, I can almost guarantee it because it's the only instance in this data set. All right, so instead of taking all the data, we know the plum's an outlier. We could just take it out. We build the model, and now we're going to get something that generalizes better. You have to remember the idea from this modeling is you're trying to start with specific data points to build something that can apply to the entire input space in a very general way, and so it has to be able to generalize. All right, and having these outliers affects its ability to generalize. You get this data that doesn't occur often enough, but it's going to become a signal in your model, and this is the only 6-centimeter plum you're ever going to see, so it's not helping you. So I know it's an outlier, so I could leave it out, so that's not fair, right? If we had a huge data set, I'm not going to know where the outliers are. So how do we do this programmatically? Well, if we just don't use all the data, we'll just random sample. Okay, so if I take just those 3 instances, now my 6-centimeter fruit is probably going to say an apple, because it never even saw a 6-centimeter plum, right? Okay, well, that's still not fair, right? That's not fair. I could have just accidentally picked the plum. So we do it again. Oh, sorry, that first one was the plum, right? Sorry. In this sample, I've ignored the plum. I've skipped it. And so now I'm going to get a model that's probably going to predict an apple. And we just keep doing this. So we take a different sample now. We'll take maybe those 3, and we get another model, and this one's also going to say apple as well. And the idea is we do this enough times, okay, that on average, we're ignoring that big plum. Okay, we're still getting a model that has statistical significance, but by ignoring some of the data at each step, all right, then we're averaging out the effect of those outliers. So when we do a prediction now, we get all three of those predictions, and then we use some kind of a voting algorithm to choose. Maybe we take majority. In this case, now 6 centimeter fruit is an apple. This is good. So this is something that's called bagging, all right? We build each tree with a random sample. If you went the additional step to randomly choose the features, all right, so you go down the tree, you don't use all the features anymore. As you can see, they're just choosing features randomly. Then this is actually a random decision forest. So we actually support both of those. So we can come back to the data set. And I'm just going to do a one-click ensemble because I have to go faster. All right, so the one-click ensemble by default will do bagging, and it'll build 10 trees. All right. And these little pictures this is an actual image of what each one of those trees look like. So you can actually, well, maybe you can't. That's really small. Make that a little bigger. But you can see visually each tree is pretty different, okay, by using a random sample of the data. So let's go ahead and use this ensemble to make a prediction so I can show you how the predictions work. So same way as before, we've got a form. We can put in our data. It's computing these it's computing these predictions in real time. But if we save this prediction, we'll actually be able to see how each one of the trees is voting. So you can see with that input data that I gave it, the first tree is predicting a 1 with a confidence of 85%. Second tree is predicting a 0, 0, 1, 1, 0, etc. So these trees don't agree. That's expected. And then the overall vote right now, this is plurality, so it's just majority wins, would predict a 1 with a confidence of 86%. So we're just taking the majority of the trees. We actually change this to confidence weighted, so this just gives a little more, increases the weight of the predictions based on the confidence. We can also do a probability weighting, and we actually have this thing called class threshold as well, where you can say, like, don't consider it a 1 unless 9 out of 10 trees all agree, because it's like an arbitrary constraint. All right. So did this do any better? Let's do an evaluation on this. Back to the ensemble. Same test set. Perfect. Yes. Compare these so you can see them side by side. Okay, so on the right-hand side, we have the single tree. And on the left-hand side, we have just that one-click ensemble with bagging. So you can see these metrics have all jumped up pretty significantly. All right, so very, very easy way to improve the accuracy of your predictive model. And we could go back and we could try a random decision forest. We could try adding more trees. There's quite a few options, but I'm gonna speed this up. Okay. So now I'm going to show you two of our two unsupervised learning algorithms that we have. Okay, the first is clustering. So just at a high level, the difference with the trees, what we're just doing is the predictive part. You have to just start with predicted label. You have to know, here's some input data, here's what I want to predict, and then you're getting a model back that makes those predictions for you. For the clustering is unsupervised learning, you give it unlabeled data. It's just some data. And the learning task here is to group this data by similarity. So how does this work? Okay, so you can imagine if I gave you this data and I said, okay, make this into 3 groups. You know, as humans, we'd be like, well, there you go. We're all done. Easy. All right, and this is basically what the clustering algorithm tries to do, okay? Except that you do this in a much bigger space, right? It's never 2 dimensions, very rarely. But then what you get back from the algorithm is the center of each of these little clusters, okay? So let me show you how this works. So I know that it's only 9:30, but you can see for me it's 12:35 in the morning. So it's the perfect time to talk about whiskey. So let's do that. All right, so I have this data set of flavor profiles for a bunch of different kinds of whiskey. So this is unlabeled data. It does tell you the distillery, but that's not really a label because it's different for every field. But you've got all these flavor characteristics like smoky and sweetness and body and spicy and winey, et cetera. And then there's a score 0 to 5. All right, and the clustering task here would be, okay, can we group these by similarity, right? So if I like this whiskey, maybe I like that one too because they have a similar flavor profile. That would be one thing we could do. Or maybe, hey, I don't like that one, and it's, this one's as far away as possible, this group. Maybe I'll like that one better, for example. So let's go ahead and do that. So we'll take this same source, which, by the way, I did an S3. We pulled this one from S3. And let's configure the cluster. All right, so we tell it ahead of time how many clusters we want. I'll choose this option. I'll explain what that means in a second. And let's do this. Okay, so I asked it for 10 clusters, and you can see there's this guy hanging out here. We're going to check that one out a little more closely in a second. Okay, but in this visualization, we actually these start proportional, but we push them apart to make the visualization look nice. All right, so I'm just going to walk through this visualization real quick. For each one of these little balls, this represents a group of data points that have been grouped together. This is 14 instances in here, and then this little data inspector on the side here is showing us the information for the centroid. Okay, so at the center of that cluster, we have this body of 2, sweetness of nearly 2, et cetera. And then that little histogram is giving us an idea of how the points are distributed in that cluster. It's showing you where they are in the distance from the centroid. We can actually extract this data set. Well, actually, let's look at this one. This guy. So we can lock the screen with the Shift key. And now you can see there's 2 additional buttons down here. One is we can create a data set. Oh, that's create a model. That's all right. I wanted to do that. Right. Create a data set. And now this new data set is just that one group extracted. Okay, so now we can interact with this directly. We can get an idea. The sweetness is 1s and 2s, for example. The medicinal is 1, 3, or 2, 3, and 4, so it's high medicinal, et cetera. Okay, so this is one way you can kind of understand the flavor profile of this particular cluster. But there's another way you could do this, right? So imagine that you just now label it. So you come back to this cluster and you say, what is it what's the difference in the flavor profile between this cluster 6 and all these other ones? So imagine we create a new data set that just has a Boolean. It's in cluster 6 or not. Right? Everything that's in cluster 6, we say true. Everything that isn't, we say false. And then we just build a predictive model. Well, the predictive models we create are conditional rule expressions. So what we're going to end up with is this nice little compact rule summary of all the important features that distinguish this cluster from the others. All right? It's quite easy to do, at least, unfortunately. Same idea, lock the screen with the Shift key and ask it to model this cluster. And now what we have here, this tree, is basically giving us a nice rule summary. Okay, so we can see right away here that if that medicinal flavor characteristic is, sorry guys, if it's greater than 2, all right, then it's in cluster 6. That's what that means. All right, so these are all high medicinal whiskeys. Okay, but we also have this corollary. Even if it isn't a high medicinal flavor, if it's less than 2, then we have this additional rule that if the smoky flavor is greater than 3, then it's also in cluster 6 as well. So if it has those 2 parameters, right, it's in cluster 6. So that tells you right away these are all the medicinal and smoky whiskeys. In the same way that you can create predictions, you can now use this cluster to make, you can take a new data point. It'll tell you the centroid and the distance from the centroid. And I haven't shown you, but you can also do this in batches too. So you can give us a data set, and we'll compute that for every value that's in there. So let's talk about the anomaly detector. So the difference with the clustering, we start with the unlabeled data. We want to group by similarity. And then we go to, and then we go to anomalies. So the idea here now is the same idea. It's unsupervised learning, but we want to ask the question, how are these points different? Okay, instead of how are they the same, I want to know how different is this point from everybody else. Okay, we want to find the anomalies. So it's sort of the corollary. So how on earth does this work? Right? How does this work? What do we do? So we're using something called an isolation forest. And the basic idea is you just grow a random decision tree until each instance is in its own leaf. All right? So you just do this randomly. Just pick features randomly and just build a tree. Doesn't matter. And all the instances are going to be distributed in this tree somewhere. And the points that are occurring way down here, these are the ones that took lots of data to figure out they were different. So they were hard to isolate. Right? Took all those splits to separate those two. And the ones up there took very, very little data to tell them apart. So those ones are easy to isolate. Right, so the ones that are easy to isolate, you get kind of the idea those are probably the anomalies, right? They stand out. And so you take this idea of the depth in the tree, where these points are occurring, all right, and that is giving you some idea of how anomalous they are. Of course, in traditional statistic methods, you can't just do this once, so you do this a whole bunch of times, okay, and you take all those depth scores and then rank them with an exponential function, and what we do is we give you a score back that's 0, meaning it's completely normal, it's just like everybody else, or 1 that's completely dissimilar. So let's do it. I'll show you this diabetes data set. So what we have in this data set is that you have all these medical characteristics, like number of pregnancies, plasma glucose, blood pressure, et cetera. And then there's this final predicted outcome of the doctors evaluate the patient and said, yes, you have diabetes, or no, you don't. And you could do this as a predictive task, take all these medical or diagnostic measurements and try to predict whether or not a patient has diabetes. But we're gonna do this with the anomaly detector and look for anomalies in this data set. So just do this. So just really quickly, we can see right here we got these what's showing us is the top 10 anomalies it found. Okay, and I'm going to show you this first one. We've got this diabetes pedigree is way on the right-hand side of this distribution. Okay, its insulin level way at the right-hand side of this 744 is way out there. Plasma glucose also way out there. And I think it sort of matched our intuition that if you have this high familial rate of diabetes and high plasma glucose, this strong indicators for diabetes, and yet this patient is marked as diabetes, false. Okay, and actually it turns out that if you just take out those two anomalies, then the performance, the accuracy in the evaluation of this model improves by 3%. Just take those 2 points out. But I'm gonna prove it to you, and the way I'm gonna do that is I'm actually gonna do it. So we're gonna take that data set, we're gonna build a model, take the data set, do a training test split. Not purge all. We're gonna evaluate it, and then we're gonna build the anomaly detector, take out those 2 data points, and build a model and evaluate it again. But I'm gonna do this using our API. This is actually running right now. And I'm just going to give you a high-level overview of our API, show you what this script looks like. So I didn't mention this, but we're an API-first company. So everything we do is in we implement in the back end, and we bring it to our API. That's the API we expose to our customers, is the same one that our user interface uses. Okay, so everything I just did in the UI, you can do through the API, plus more. There's usually more features in the API. I don't know if you guys can see that. That's pretty blurry. Should have done black. But so I'll go super fast. Just setting up the API connection. You can see I'm creating a source. You can't quite see, but that's just a file on my machine. And then we have this create data set. It's pretty straightforward. I'm creating the training and test set manually. Wow, you guys can't see that at all. That's terrible. Is that better? Oh, you can at least see the white now. We'll do that. But so no, you can't. Now you can't see that either. Believe me, you can do it. This is. I didn't mention it. This is just Python. But anyways, you can see it's done. Of course, because our UI sits on top of our own API, then everything I just did through the API shows up in the UI as well. Okay, so all those data sets, evaluations, everything show up in the UI. No problem there. And so we can see, for example, our 2 evaluations should be here. So we have one that's just the evaluation of the model using everything, and the other one with the clean data set where I just took out the top 2 anomalies. So let's open these and have a look. Yep, thank you. And now we can see these side by side. So on the right-hand side is just with those 2 anomalies removed. All right, so we've improved our metrics by 3%, as promised. No worries. And then I'll just give one closing nod to our command line tool as well. All right, so on top of our backend, we provide the API, same API that we use is the one we expose to our customers. We have bindings in several languages. Okay, where now this allows you to basically treat us like a machine learning API, right? So you can come in, you can do stuff in NumPy or whatever environment you like, and then when you need to do a predictive piece, it's very easy to just connect to the cloud and offload this to our very large infrastructure. But then sitting on top of our Python bindings, we also have this command line tool called BigML, where you can do everything just with one command line, right? So you can just give it a CSV file or whatever and run one command that models, evaluates it, does cross-validation, and various other statistics in there too. So if you guys sign up, create an account, then use this code This PAPIs 2014 will give you a free 1-month subscription. If you already have an account, just shoot us an email at info@bigml.com, and we'll hook you up with a free subscription as well. We do have a development mode where everything that's under 16 megs is free. So there, I'll stop there. Yeah.
Brought to you by Form Systems, the leader in API and cloud gateway technology.